Welcome everyone. In this video, I want to go over the solution of the sample exam number 1 and explain problem by problem how to solve them. You can, once you watch this, please go ahead and try to do it yourself, and you can then check the answers again. So let's go over the first one. The first one, you're given 3 vectors, and that's in R3. We know the first question is pretty straightforward. It says compute 3 times W, 3 times U, 2 times W, and then add them. So 3 times U, again, you take 3 and multiply it by the components. So you get that vector. 2 times W, you take 2 and multiply it by W, by the components of the W. Then 3U plus 2W, you just add the 2 vectors and you get negative 19, 1, and 6. This means the magnitude of W, or the norm of W. So that's given by the first component squared plus the second component squared plus the third component squared, and you take square root of that. So it's 4 plus 25 plus 0 squared of 29. Third, number C, or the third question says find the unit vector parallel to U. To find the unit vector parallel to U, then you can just find that. So just take the components and divide that by norm of U. So you find the norm of U, and you take each component and you divide it. And another parallel vector to that, you can just, which is a unit vector, you can just do negative U, and you get these 2 vectors. One answer is good enough because this is a unit vector and is parallel to U, and that's also a unit vector, has the opposite direction, but it is parallel to U. So any of those answers are fine. Number 2, find Cartesian equation for the plane in R3 determined by the span of these 2 vectors. So we know, first of all, know the span of 2 vectors in R3 for 2 vectors that are not parallel or are not parallel. The span of those 2 vectors can be plane passing through the origin. So how do you find that? You can put x, y, z equals to r times the first vector plus s times the second vector. And you simplify that, so it's 7r plus 2s. From here, the second component is 3r minus s, and the third component is negative 2r plus 7s. So you know that x is that, y is the second one, and z is the third one. From here, what you want to do is eliminate r and s and get an equation with x, y, and z. To do that, you can take the first equation, multiply, add 2 times the second equation. So if you do that, s is canceled, you isolate r, and that's r. Then you go to the second one and the third one, and you eliminate s again. So you do 7 times the second one plus the third one. And if you do that and isolate r, you get 7y plus z divided by 19. And you put these 2 equations equal to each other because they both represent a value for r. Then if you simplify, you get the equation of a plane, and that equals to 0. Obviously passes through the origin. So that's the answer. Number 3, prove that the set of vectors in B, 1, 1, 1, and 1, 1, 0, and 1, 0, 0 are linearly independent. If you want to show that a set of vectors linearly independent, so you do the first vector, you can do A, C, doesn't matter. C1 times the first vector, B1 plus C2 times the second vector, plus C3 times the third vector, and you put that equal to 0. Basically, you solve the homogeneous system, and you have to get the trivial solution. In this case, if you call C1, C1 equals to C2 equal to C3, and that should be equal to 0. So you write the matrix for that, and you can do the calculate the RF, or you can use your calculator. And at the end, you get that matrix. So that means C1 equals to 0, C2 equals to 0, and C3 equals to 0. It has only the trivial solution. And that's also called the identity matrix. So each time you solve the homogeneous system and you find the RREF of the matrix and you end up with the identity matrix, and that means 1 in the diagonal, zeros, the upper and lower triangle. We are going to see this in detail. That means it has only the trivial solution, therefore the vectors are linearly independent. Another way to show that, you can write the matrix and find the determinant of that. That's a 3 by 3 matrix. Some of you probably know how to calculate the determinant, but we are going to learn this in detail. And if the determinant is not equal to 0, then the conclusion is that the vectors are linearly independent. So if you are comfortable by using this, you're more than welcome to do it. And again, the next sections or chapters, we are going to talk about determinants in detail. Number 4. So suppose that U is a vector, a non-zero vector, and A, well, that's maybe the first component. You don't have to worry about that. It's not equal to 0. Show that the line L, the span of U, has the Cartesian equation y equals to 5/4. That's a pretty easy. If you want to find that the span of U is t times AB, so in this case it's going to be t times 4, 5, the components of that vector. You isolate x, which is 4t, and y is 5t, and from both of them you isolate t, it's x/4 and x/5, then you put them equal to each other and you will get that equation. So, or you can just plug in, it doesn't make any difference. That's pretty simple. Number 5, consider the two lines. We have x is 5 plus 2t, y is 3 minus t, and z is 3t. And the line, the second line, the x component is 7 minus 4s, and y component is 5 minus 2s, and the z component is 8 minus 6s. Show that the lines are parallel. So a couple of ways you can do that. Again, for line 1, we have this equation, and for line 2, we have that equation, and we can separate them. So if we separate them, you get 5, 3, 0 plus t times 2, negative 1, 3, and L2, 7, 5, 8, and you get s times negative 4, 2, and negative 6. So here t and s are constant. Now, the vector direction of these two lines are these two. So if we can show that these two vectors are scalar multiple of each other, then you can say that the lines are parallel. So what you can do, you can just simply write d1 equals to 8 times d2, or d2 equals to 8 times d1, and if you solve this one by one, you're going to get negative 2. Or you can say t times d1 should be equal to s times d2. So, and if you write that and you solve for t and st, you're going to get negative 2, and s is going to be negative 1. So, and here how you can solve the system, or you can write the symmetric equations of the line, and you do that, then you can find the direction vectors. So then you can see one of them is a scalar multiple of the other one. And I did that for a homework problem the other way, so you can double check. Find a Cartesian equation for the plane that contains the two lines. So part B, if you wanna, so you have D1, the vector direction of one line, or yeah, both of them, you can just take that. So then you can find a vector from D1 to the line 1 to line 2, the components of that vector, what you can do is just subtract the coordinates of the points on each line. So you get 7 minus 5. And again, if we come here, it's 7 minus 5, 5 minus 3, 8 minus 0. So if you do that, so you get 2 to 8. You know, if you take D1 and cross it by V, that vector, then you're gonna get a vector that is perpendicular to D1 and D2 at the same time, and that's the normal vector. So you can take the components of that vector and take the coordinates of one of the points and say -7 times x minus 5 minus 5 times y minus 3 plus 3 times z minus 0. Simplify and you get -7x minus 5y plus 3 is equal to -50, or you can change the sign. 7x minus plus 5y minus 3 is equals to 50. And again, please check the homework problems. I did a problem in detail, very similar to this one. Number 6, find the parametric equation for the line that contains the point 5, -2, and 1, and it's orthogonal to the plane 3x plus 7y minus 4z. So where does the line intersect the plane? So now we have a point and we have the coordinates of vector n, that plane. So now the point is given, then you know that the parametric equation of a line is given of the point plus t times the direction vector. So we have, what we can do is take the point, find the equation of that line, plus t times that, and the parametric equation of the line x is going to be the 5 plus 3t, and y is going to be -2 plus 70, and z is going to be 1 minus 4t. So now, since n is orthogonal to the plane, then this line is going to be parallel to n, and it will be orthogonal to the plane also. Now let's see where this line intersect. You have x, and you have y, and you have z. You can go to the plane and substitute the values, the expressions for x, y, and z, and solve for t. Once you solve for t, then you can come back to this equation and substitute t. And if you do that, you get those numbers. They're kind of big fractions, but that's where they intersect each other, the plane and the line. Next one is a proof by using vectors. It says prove that the magnitude of the cross multiplication squared equals to the magnitude of u squared times magnitude of v squared minus u dot v squared. Let's start. So the magnitude of u cross v squared, so we can write that. So u cross v, first of all, can be written as u magnitude of u times magnitude of times sine theta. So that's a formula. Please watch the recording on cross multiplication. If you square that, that means you can take this and multiply it by itself twice. Then this can be used as the magnitude of u squared times magnitude of v squared times sine squared. But sine squared is the same thing as 1 minus cosine squared. So instead of sine squared, you write 1 minus cosine squared theta, or sine theta squared. Then you can distribute that, so you get the magnitude of u squared times the magnitude of v squared minus the magnitude of u squared magnitude of v squared cosine squared theta. So, however, what is this again? Check the lecture on dot product. That's how you can write dot product. Dot product is magnitude of u times magnitude of v. U dot v is magnitude of u times magnitude of v times cosine of the angle of those vectors. And if you square that, that's what you get. So what you can do, instead of this expression, you can substitute that, and it's proven. You get the same answer given in the problem. Use the minimizing number 8 minimizing theorem to find the subset S double prime of the set S. So S double is as small as possible that have the same span of S. Now, if you are given a set of vectors, here we have 5 vectors. So if you write it like that, so we have V1, V2, V3, V4, and V5. So, and we are in R6. Each vector has 6 components. The best way to do this, write the columns. So this is your V1, V2, V3, V4, and V5, 1, 2, 3, 4, 5 vectors, and find the RREF of that matrix. And again, use technology for that because it's very long. Now, we know for sure that the pivot columns are linearly independent. So what you can go to the original one, and instead of take those vectors that match, so in the original one, and these are the first vectors. So for sure, these 2 vectors are linearly independent, and they are going to have the same span as S. So this is our S prime, and then if you do S minus 8 prime, you're going to be left with 3 vectors. So now you can see, go to RREF again, you can see that V3 can be written as 2 times, just 2 times, negative 2 times the first vector, and that's all we have because the rest are 0. Now V4 is this vector, which is the same thing as negative 1 times that. It's going to give us negative 1, and 1 times the second one is going to give us that. So you can say just it's V2 minus V1. So in this case, if we call those C1, C2, write it nicer, C1, C2, C3, C4, and C5. So we know that if we do C2 minus C1, that vector minus that vector is just going to give you that vector. So C4. Therefore, you can say V2 minus V1 is V4. For V5, let's look at it. I can multiply this by negative 2 and multiply the second one by 5. So it's going to be negative 2C1 plus 5C2, which is the same thing as negative 2V1 plus 5V2 if you go to the original set. So the RREF is going to help us to find the relation between these 2 vectors. Number 9, use the minimizing theorem. So basis for the subspace version to find a basis for that. So here it's almost the same problem. You are given a set of vectors, and these are, we have 4 vectors. 1, 2, 3, 4, actually 5 of them. V1, V2, V3, V4, V5. The first thing you want to do is find the RREF. Write this as the columns of the matrix. Find the RREF, then you know these 2 vectors are pivot vectors, then they are linearly independent. So if you want to actually, we have that one, the pivot one, and that one, and V4. So these 3 columns are pivot columns, therefore they're linearly independent. So the corresponding vectors are going to be linearly independent. So if these vectors, the vectors are linearly independent, then they can form a basis. So, and the dimension of that of a basis is the number of vectors in the basis, and it's 3. So I have a recording on this in detail, the basis and dimension plus. Please watch that and you'll see. Number 10, you're given a matrix A and the RREF, and you're given the RREF R prime of A transpose. First of all, the transpose of a matrix is when you interchange the columns and the rows. So you have A, the RREF of A, and the RREF of the transpose. So find the basis for the row space. For the row space, if you want to find the basis, you go to RREF and you just take the ones with the leading one. So is that and that. So a basis for the row space will be this vector and that vector. You can just write it down. And a basis for the column space, you just go to RREF and take the corresponding vectors to the pivot vectors. Here the first and the second are pivot columns, so that and that. So the first and the second vector in A are gonna be the call space. So, and as you can see, we have it here. Then the null space, what you need to do is go to the RREF, just solve this. So you can call this x1, x2, x3, x4. Rewrite the system, and what we have, two non-pivot columns. So x4, x3 and x4 are gonna be our free variables. Rewrite the system and you can solve it, and if you do that, you get these two vectors. Now, a null space for the transpose is pretty straightforward. You can do the dot product with the call space of n, you should get 0, or simply, and I did that here, so you can go, this is the RREF of the transpose. So you write that and you put x1, x2, x3. We know x3 is going to be a free variable. So x3, you can call that t. x1 can be written as x1 minus 3x3 equals to 0. So you isolate x1, and here you isolate x2. So you get 3t minus 5t and t, and it's t times that vector, and that's a basis for the null space. And it has only one vector, so the dimension is going to be 1. Now the rank of A is the dimension of the call space or the row space, which is 2. They each have 2 vectors. The nullity of A has also 2 vectors. The rank of A plus nullity of A is 2 plus 2, which is 4. And the number of columns of A is also 4. Please watch that lecture also on matrix spaces, and this is gonna make a lot of sense. Okay, I think that's it for the sample exam number 1. Once you watch this, now try it yourself and double check the answers again. Thank you for watching, and I'll see you in my next video. Have a good one, everyone.